Bismillahirrahmanirrahim. Today's lesson is the lesson from the vector algebra. We have already started. We will discuss the product of two vectors. We call it as dot. There are different ways we can have. For example, I have the vector A and B. I want to take the product. I look on the result. I have this vector A and vector B. I want to multiply it. I look on the result. For example, when I multiply, I get here the scalar. Scalar means the value. Or the second is when I multiply in such a way that I will get a vector. The result is a vector. We define in such a way that it becomes the vector. So if we get a result as scalar, we call it a scalar product. We call this one a scalar product. And we are having here the result as a vector. We call it as vector product. So we are looking on the result. According to the result, we are going to name the product. Now, we can have the notation for this one. We have vector A and B. When we have scalar product, we say A dot B. And here we say A cross B. As we are writing here A dot B, so we say is a dot product, as I give the title. Also, we call it as a dot product. And we have used the cross. So we call this one as vector product or say cross product. So this is the name for the product we are going to define for two vectors. Now this dot product, sometimes some of the books they just define it as inner product. We call this an inner product also. So it's having three names. We call it as dot product, we call it as scalar product, or we call it as inner product. Whereas the vectors we are having here, when we multiply two vectors, we get a vector. We say it is a vector product, or we say A cross B, or we say the cross product. So we take the definition of each of them. First we define the dot product. So we say, as we have this definition 1 for defining the dot product. So as I said, we take the definition in such a way that we get the result as a scalar. So we say we have given two vectors. Vector A is A1I, A2J, plus A3K, we write in the component form, or we write in the bracket form. Where vector B is B1I plus B2J plus B3K. I say I take the dot product, I define it as A dot B. This is the multiplication of the components. This is A1 B1 plus A2 B2 plus A3 B3. So this way we will define our product. We say this is our dot product. As the result, we are getting scalar. So we say it's scalar product, or we say it's as an inner product. So I take an example to explain further. That we're given here two vectors. We take the example. We get vector A. Vector A is 2I minus 3J plus 4K. And we're having another vector B. Vector B is I plus 2J minus 2K, and we want to find the dot product. Find dot product. So dot product, or we say scalar product, or we say find A dot B. So a solution of this one, we write A dot B, we apply our formula, we multiply component wise. His component is 2 and his 1 is 2 into 1, A1 B1 plus A2 is minus 3 into B2 is 2, and plus A3 B3, that is here 4 into minus 2. So multiply it, I get here 2 minus 6 minus 8, I get here 2 minus 14. Now my result is minus 12. So it's a scalar. So say A dot B is equal to minus 12. As I said, the result is a scalar, not a vector. Vector is in this form. Vector is having the components I, J, and K. But here we don't have the components. Simply we just multiply it components wise. This A1 B1, A2 B2, A3 B3. 2 into 1 is 2. Minus 3 into 2 is minus 6. Minus 4 into minus 2 is minus 8. 2 minus 6 minus 8 is minus 12. So that is the idea of the dot product. We have given the example. We take more examples, and I give you the properties of the properties of the scalar product also. So we are going to take the other definition. This is our definition 2. We given two vectors. We have vector A and B. And we say this is my vector A and this is my vector B. Here is my vector A and this is my vector B. Angle between these two vectors is theta. So theta is from 0 to 90, 0 to pi by 2. So we can say we can define the dot product of this one in terms of theta. We define here A dot B, this is the second definition, is equal to magnitude of A into magnitude of B into cosine of theta between them. So the magnitude is scalar, magnitude of B is scalar and cosine theta is scalar. So the result is a scalar, second definition of that one. From this definition we can get many results. For example, I can find the value of theta between these two vectors. I can write from this equation my cosine theta is equal to A dot B over magnitude of A into magnitude of B. So my theta will be equal to cosine inverse of A dot B over magnitude of A into magnitude of B. Now here we can have some more results when we take here that when cosine theta, when theta is equal to 0, so we know cosine theta is equal to 1. And when we have cosine theta is pi by 2, the cosine pi by 2 is equal to 0. We can see it here. This is my vector B and this is my vector A. I say the angle between these two is pi by 2. And here when we say this angle between these two is pi by 2, so we can write here A dot B is equal to 0. Why? Because we know our cosine pi by 2 is 0, then 0 multiplied magnitude of A magnitude B is 0. So we can say this is number 1, this is number 2, number 3, when A dot B, the dot product is 0, then if this is 0, then we can say the angle between them theta is equal to pi by 2, I say 90 degree. I will say A is perpendicular to B. So they are orthogonal to each other. We say they are orthogonal to each other. I will say they are perpendicular to each other because we can see it here. The angle is pi by 2, then cosine pi by 2 is 0, and we get A dot B equal to 0. I will say when A dot B equal to 0, then our theta is equal to pi by 2. I say A and B are orthogonal. So this is another property we can see. We can find it from here. Now we can have here, we can just discuss the properties of the determinant, and we can have some important properties of this dot product. So I can just write it here. Properties of dot product. So number 1 is commutative. That's here we can having A dot B, and it's same as we can write B dot A. You can see it here. We take here A dot B, this is my A dot B. If I want to write B dot A, then my B dot A is equal to B dot A is equal to B1 A1 plus B2 A2 plus B3 A3. If we write here 1 into 2 is same as 2 into 1, 2 minus 3 is same as minus 2, 3, 4 into minus 2 is same as minus 2, 4. So we'll get the same result. When we're having A dot B, he's there, A is equal to 12. I find here B dot A, then B dot A is also equal to minus 12. So we say A dot B, so we say it's commutative. We say it is commutative. That means we can interchange the place. Instead of A dot B, we can write B dot A. The second one is the result that we are having this rule, number 2. We are having here vector A multiply with the sum of the vector B and C, same as we multiply A with B and A with C is allowed. And this is known as distributive law, that we can just, when we find here, first the sum and then take the dot product, is same as that we take the dot product of each of them and add them, we get the same result. So we call this rather as distributive law. This is distributive law. So this also allowed in case of the dot product. So these are two laws we have seen. The third law we are having here, that we are having here two vectors A and B. We are having the vector A and B, and we are having K as a scalar. So we can write here the position A dot K B, where K is scalar. A is a vector, B is a vector. So this K I can write anywhere. I can write here Ka dot B, or I can take K out. We can write A dot B. Here K is scalar, so that's also allowed. In case of the dot product, we can have a scalar value, and we can write the scalar value anywhere we like. So next is the idea that we are having two vectors, A and A, and multiply them. So we know that A dot A will be equal to what? We're having the vector A and we're having vector A. I want to take the dot product. What will be A dot A? A dot A will be equal to A1 plus A2 plus A3. That's equal to A1 square plus A2 square plus A3 square. This what? This magnitude of A. Because we know if we take vector A, I want to take the magnitude of vector A. So I have here vector A is equal to A1I plus A2J plus A3K. So what's the magnitude of A? Magnitude of A is equal to root of, we're having here A1 square, A2 square, A3 square. So we're having here this, as I wrote there, that's here A1A is equal to this. So we can write here number 3 and number 4, we can write that we are having here A dot A is magnitude of A whole square is always bigger than equal to 0. When A is 0, this is equal to 0, is always bigger than equal to 0. So this is the ideas we are having related to the properties of the determinant of the dot product, that A dot B is equal to B dot A, commutative law. Then A dot B plus C is equal to A dot B plus A dot C, distributive law. K is a scalar, and we can write our K anywhere with A or with B or outside. And we take A dot A, we have seen this is equal to magnitude of A whole square. We can have here this A dot A, this A square is equal to A dot A. So we can write that in there. So that's the idea for the having the properties of the